This is my lab report for Physics 2212 Lab 4 Circuits. So in this lab, I used a computer simulation to create circuits and predict their behaviors when using resistors in series and in parallel. I also used voltmeters and ammeters to measure the values of potential differences in current in the circuit and observe the behavior of ohmic resistors and capacitors. The physics principles I used to solve problems in this lab were the loop rule, the node rule of current conservation, and Ohm's law. As a summary, I observed a current in the simulation very similar to my theoretical calculations and observed a higher resistance of the resistor in the simulation than I expected in theory. In a resistor-capacitor circuit, my theoretical and observed values for RC were equal. So I started with a circuit containing two 1.5 volt batteries and two resistors of 47 and 100 ohms. Here's my theoretical calculation for the current using the loop rule, an application of conservation of energy. So since the two observation points before and after the resistors are in series and the current's in a steady state, the current should be the same throughout. As you can see, this is the same as was measured from the ammeters in the simulation. When the ammeter is inserted backwards, the current measurement is the same. Since current is a scalar quantity, it doesn't change when I flip the ammeter. When I replaced an ammeter with a voltmeter, the first ammeter read 0 amps because the voltmeter has extremely high resistance, so no current can flow, and the voltmeter reads a potential difference of -3 volts because the loop is practically open. The potential on the right is 3 volts from the EMF, but it can't flow through to the left. Here's the chart from my readings of the potential at each point relative to point A, measured by my voltmeter when the circuit is closed as shown in the picture to the right. By the loop rule, the sum should equal 0 volts, and it does, as you can see. By point F, it's down to 0. When I attach the voltmeter, the ammeter reading doesn't change because voltmeters have a very high resistance, meaning practically no current travels through them, so the current going through the rest of the circuit stays the same. This is true no matter where in the circuit I put the two ends of the voltmeter. When I added an ammeter to the circuit in parallel, the current through both ammeters increased because now there was an alternate path with less resistance for the current to go through, which is an application of the node rule. In the next part, I calculated resistance from the observed values of delta V and current I using Ohm's law. The R values I got for the two resistors were higher than the theoretical values of 47 and 100 ohms. As you can see, for the 47 ohm resistor, I got 47.95 ohms, and for the 100 ohm resistor, I got 102.05 ohms, and for the wire in the ammeter, I got 0 ohms as expected. Next, I made a circuit with a resistor and capacitor and a 9-volt battery. I observed the magnetic potential across the capacitor as it became charged by the battery over time. Since the magnetic field of a capacitor is in the opposite direction of the magnetic field from the circuit, it slows down the current, and eventually, once it's charged with the 9 volts, it causes 0 current to flow and the light bulb doesn't glow. Here I used my observations over time of the potential across the capacitor as recorded in the table on the left to calculate the RC value by manipulating the loop rule or the energy conservation equation for the circuit. So I solved for the time-dependent delta V, and then I could solve for T over RC. So when I graphed ln of V over V naught versus time, the slope would be equal to -1 over RC. So using this, I found my value for RC, which was equal to the theoretical value. They were both 6.0. So I found in this lab that the resistance of a resistor is usually higher in the real world than it is theoretically due to outside factors or resistance from the wire that's neglected in theory. If I did this lab in real life and used an actual ammeter, the ammeter would likely have a higher resistance than in theory, and the current would be lower than expected because of it. If we didn't use a resistor in the RC circuit, the time to charge the capacitor should be 0 seconds. We can get this by differentiating the loop rule equation again to find that dq dt is 0, so the capacitor will immediately have a charge of 1.8 coulombs. In reality, the wire will carry some resistance, so the capacitor should take at least some time to charge once the circuit is closed.